Alright, today we are talking about the Unit 1 test review. I will do my best to answer every question as if you had a problem with every question. Now, do I think you will? No, but I still want you to have that opportunity to get help when you might need it. So starting with the first problem, they're asking you which of the variables is quantitative. You need to remember that if they're talking about quantitative, you are looking for something that you could possibly evaluate as if it was data. Could I find a mean, median, mode, range? Now, when we're talking about class, although class might also be described as 11th, 12th grade, you're not going to find a median in the grade. Well, you might find a median, but you're not going to find a mean. You're not going to find an average. Grade point average, that in and of itself tells you, hey, look, something that I can actually calculate. If the student is in an AP class, it's a yes or no question. Same thing with whether or not they've taken the SAT. So yes, no questions are not quantitative. That's why the answer to this one is B. On number 2, which would you most likely follow a normal model? And again, a normal model is something that you would expect to see bell-shaped. Now, if we're talking about family income, if you know anything about the United States right now, you would know that the distribution of family income tends to be more like that. We have a big dip in the middle. Now, that's definitely an exaggeration, but you have a lot of people on the low end, and actually you have, it's probably a bad description, it's probably more like that. A lot of people down here, very few people up on the high end. So that is not normally distributed. Weights of adult male elephants, I have a feeling those are probably close to this. Scores on an easy test. Remember, if it's an easy test, it's going to skew your data. So you're going to have a lot more on the high end. Normal models are only for symmetric and unimodal data points. So the answer to number 2 would be C, weights of an adult male elephant. Number 3, we're given the mean and the median, and we're saying, okay, we've got one student whose score was an 85, should have been gone up to a 90. Now that 85 is above both the mean and the median. So what that's going to do is that's going to affect your mean score, but not your median score. It will affect the mean because the mean is the sum and then of all of your data points divided by the number. Now, the number is not changing, but the sum of your data points has been increased by 5. So that's why the mean will change. We're not changing the number of values that we have, so the median itself will stay the same. So we're looking for the one that says the median will stay the same, but the mean will increase. So that's C. Number 4, the weight of baby pythons, approximately normal, means we get to use everything that we know about our normal curve, distributed with a mean of 31.8 grams, a standard deviation of 2.39. We're looking about the percentage of baby pythons between 25 and 33 grams. Now, on the AP test, since most of that work will be done in the calculator, you do need to show an understanding of what the heck they're talking about. So you would draw a normal curve. You would say the fact that the mean, 31.8, is somewhere in the middle. And the ones that we're talking about lie somewhere between 25 grams, and if it's a standard deviation of 2, it's going to be over here a bit, and 33 grams, it's just going to be about here, and we're looking for that area in between. Now, if I go to my calculator, since I'm looking for the percentage, I'm going to use my my normal CDF. For your screen, you will actually be able to type these values in. So I'm going to say my lower area, my upper area, my mean, and my standard deviation. This is just an older operating system, which is why you do not see the drop down. And it calculates out to be 0.68997. Well, the closest thing to that, very, very close, is A. Now our ogive, also known as a cumulative frequency chart. We are looking for the interquartile range. The interquartile range goes from the 25th percent, which would be actually a little lower than that, and the 75th percent. And so we're looking for about here to here. So my upper end, I am going to say that's probably, we're just estimating, so I don't need to go too crazy with this, but I'm going to say that's 175 minus the lower end, which looks to be about 75. So I would say the inner quartile range to be about 100. On number 6, we're looking for the mean speed. Okay, so we've got 18 men whose speed was 72, 30 women going 64. Now this problem was on the quiz. We've got to make sure we understand how to do these. So we're going to take, actually let me change this to this. We're going to say 18 times 72, because remember average is all about sums, and 30 times 64. We're going to divide all of that by the total number of people, which is now 48. So 18 times 72 plus 30 times 64 divided by 48, and I get that my mean is 67 miles per hour. When we're looking at histogram data, you want to make sure that you're very careful as to how you're describing this. Now this graph looks like it's being pushed from this side, or it has its tail on the lower end. So that means that this data is skewed left. So I'm not going to choose that one. Because it is skewed left, that is going to pull the mean in the direction of the skew. So it is going to make the mean probably smaller than the median. Now also, because it's skewed, when it is skewed, we use median and inner quartile range to summarize. The only time we use mean and standard deviation is if the graph is symmetric and unimodal. Well, it's not symmetric, so we're not going to use those. So that means 2 and 3 only are right there. If we collect data from 50 male students, which variable is categorical? Remember, these are things that you're going to have labels for. And since I do not have labels for most of these, this one should be quite easy. Eye color is categorical. For this bimodal problem, you got to kind of think carefully. Bimodal means we're going to have a high group and a high group, and we're probably going to dip down in between them. Now if I'm talking eye color, we've already said that that is categorical, so we're not going to describe that using modes. Head circumference, most people will fall in a specific range, so I'm not going to say head circumference. Hours of homework done last week, well, for that one you can kind of think in all sorts of different ways. You might even think that this is fairly uniform, that you might have a lot of people doing very little homework, and then you have people who are crazy doing hours of homework. If I'm talking about number of cigarettes smoked daily, we're going to have people either doing pretty much no cigarettes or people who smoke a lot of cigarettes. So I have a feeling that would be our bimodal one, because we're going to have the non-smokers and the smokers. And that's going to be two completely different groups, so we're going to see two completely different humps in our graph, two different modes. The number of TV sets, we're not looking really at different groups. Even if you look at economic standings, most people nowadays do have at least one TV, and then you go kind of crazy off the end about people who have multiple TVs in each room. So for number 9, I would argue that the number of cigarettes. Whereas I would say head circumference is probably going to be the one to follow a normal model, simply because I have family members with big heads, and I have seen the normal curve that goes with that. Most heads will have a certain circumference, and you'll have your smaller people, and then you'll have your bigger people. And so they do tend to be normal model. Alright, what's true of the data whose distribution is shown? Again, we're pushing from this side. Tail is on the right, means we are skewed right. When you are skewed, it's going to pull your mean in the direction to where your tail is. So that means my mean is probably going to be higher than the median. So I am not going to talk about that one. And as it is slightly skewed, we should probably not talk about mean and standard deviation with this one. So for number 11, I would say A. Another one of those multiple data points, find the new mean. Well, if we have 30 males, 20 females, a total of 50 people, 30 times 6, plus 20 times 9, 360, divided by 50, my new mean is 7.2. For this one, we're talking about who ranks higher in their own league, George or Bill. So let's see how we do. Whenever we're comparing two separate groups, we need to do that using our z-scores. You can draw a picture, you can work that all out, but frankly that's going to be a lot more difficult. It's simpler to find the z-score, and your z-score is the value, George was 180, minus the average, his league is 150, divided by the standard deviation. 180 minus 150 is 30. I should just done this by hand. Dividing it by 20 is going to give you 1.5. So George's z-score is 1.5. Bill's average was 190 his score was 190. His average for his league is 160, and their standard deviation is 15. So that's going to be 90 minus 160 is 30 divided by 15 is 2. Now comparing z-scores, Bill has the higher z-score. So that means Bill did better. So what that allows me to do is cancel out these two and just take a look at the two reasonings they give me. Now it says Bill's score is higher than George's. Well, technically it is, but that's not why. Bill's standardized score, and that's what the z-score does, is it converts to a normal ruler and allows us to compare. His is higher than George's, so that tells me that B is the answer. If distribution is skewed to the right with no outliers, skewed to the right means you're going to have a tail on the right hand side, and it's going to ask you, where are these data points? Well, whenever we're skewed to the right, right is a higher value, left is a lower value. So this here is my median. My mean is pulled in the direction of the tail, so my median should be over here. And comparing that to the right is higher, so that should be that my mean, and all of these are starting with the word mean, is greater than the median. So the mean is greater than the median, that would be D. Now we're talking about the normal model of rainwater, and when we're told a z-score is 1.8, remember we're talking about, when we're looking at our normal model, we have our mean in the middle. A z-score of 1.8 is going to take you out this way. Z-score is not a pH. They do not have labels. It is a standardized ruler. We are looking at, let's see here, 1.8 higher. We don't know that. This is not a ruler according to these labels. So it's not this one. We don't think it's got a pH of 1.8. We'll come back to what the word varied means. 1.8 times that of the average? Nope, it's 1.8 standard deviations higher than the average. What they're trying to talk about this is they're saying the standard deviation is 1.8. Varied just means how it's stretched. But this is the z-score. This isn't the standard deviation. So the answer is B. Number 16. His score was in the 64th percentile. Please do not confuse that with a 64%. So we cannot say he scored a 64% on the test. Being in the 64th percentile means that he scored better than or the same as 64% of the students in the class. And my dog is getting jealous that I am talking to you right now, because the 64th percentile would be right about here, and that's 64% lower than. We have no clue how many questions he got correct. We do not know if he failed the exam or not. And because we know this one is true, that eliminates E. So the answer is B. Yes, my dog says hello. Which of the following has the largest standard deviation? Standard deviation is a measurement of variance. Variance talks about how spread from the mean you are. The mean, we would assume, or the median, to be somewhat in the middle. So I'd assume the median to be there. This one's going to be skewed left. So the mean would be pulled to the left. I'm sorry, but it wouldn't be there. It would be probably right about here. Mean would be here, mean would be here, and mean would be here. The greater the standard deviation, the more weight you will have far away from the center. Well, you've got about half the weight in the middle and half the weight on the ends. So while that varies, the standard deviation can be greater in some of the others. If I look at this, the heaviest weight is farthest from the mean. And the heaviest weight here is stacked a little bit closer. So if I were to rate these in the greatest standard deviation, I would say that this one's the largest. So I'm going to select D for the largest. Then I would say it'd probably be a toss-up between E and A as to which ones came next. Then the second smallest deviation would be this one, because we have some areas where we have quite little weight. And then the lowest standard deviation would be this one. Again, standard deviation talks about variance. This has the most weight away from the middle. That has the greatest variance. These guys are all talking about using your calculator to find your lovely stuff. The big thing is you illustrate with a picture. That means draw your normal curve. Now you can see my normal curve is not pretty. Yours doesn't have to be either. Do not draw semicircles. Okay, so for this one, the mean is 55. Standard deviation is 4.83. So a snowfall less than 60, that's just over one standard deviation. It's going to be right here, but that's less than. So I'm looking at this side. So what I'm going to do is I'm going to go to my calculator. Again, I'm going to do the normal CDF. Now, because I'm talking about regular stuff here, actual things, I still want to use numbers that go beyond reasonable. So I'm going to stick with the negative 99 for my low. I'm going to go to 60 for my high. My mean is 55. My standard deviation is 4.83. And so I'm going to say roughly, and this is saying probability, so probability is a decimal, 0.8497. Probability that your snowfall is greater than 57. Again, 55 was my middle. 57 is less than one standard deviation above, and we are talking greater than. So again, I'm going to go to my normal CDF. I'm going to start at 57. Now because positive 99 isn't that much greater than 57, I'm actually going to go to 999 for my upper bound. My average is still 55. My standard deviation is still 4.83. And so I'm going to get roughly 0.3394. Now if you take this big enough, this number big enough, you won't see a difference within these first four decimals. You might see a difference further out, but that's why we take it up to such a big number, to see proportionately a really, really large difference. Now this one is quite simpler. We don't have to worry about upper and lower bounds. My mean is 55. Between 31 and 57. Well, 57 is going to be right about here, but 31 is going to be all the way out to the end. Because each of these groups, remember, are just shy of 5. So 50, 45, 40, 35. It'd actually be more than one more standard deviation out. That doesn't matter too much. We still want to make sure that you know that it's between two things. So I'm going to put the lower number. the higher number, standard mean, and standard deviation. And voila, it works out to be about 0.6606. Watch your rounding. Now this one, they're telling you the probability that the snowfall is greater than X. And that probability is about 0.42. If I'm looking at 55, we're saying, remember, at that mean, half the data lies greater than it. And we're saying the snowfall is greater than this. So we're looking somewhere about right here. Remember, your calculator and the tables, if you chose to use it, always talk about the probability that something is lower than. So for this one, I'm going to take 1 minus 0.423, and I'm going to get 0.577. Now when we're talking about probability, I'm going to use my inverse normal. And since I have my probability, I just do 0.577, the mean, and the standard deviation. Hello, Emmy. And so that I get the amount of snow is approximately 55.9 inches. Okay, remember, given a probability, use your inverse normal. Finding a probability, use your normal CDF. Now, one of the big suggestions that I have, and I really can't stress this enough, when you have a 5-number summary or something with even more information than that, go ahead and sketch what your box plot would look like. So, for my box plot, I'm going to sketch it out. My minimum is 15 and my max is 200. So I'm going to go ahead and put 200 up here. I'm going to put 0 down here. That means 100, 150, 50. So if I were to sketch this, my minimum would be down here. My maximum would be someplace up here. We need to see if they're going to be outliers. My median would be 50. Quartile 1 would be 30. Quartile 3, whoa, that's a big jump, 110. So there's my box. Let's calculate my outliers, my fences. So I'm going to say my inner quartile range. Quartile 1 minus quartile 3 minus quartile 1 gives me 80. So I'm going to say 30 minus 1.5 times 80, which is a negative number, I don't care. And then I'm going to say 110 plus 1.5 times 80. And so I'm going to come up with 230. And so my fence actually lies beyond my greatest value, so I do not need to put any outliers on here. So there are no outliers, no values are greater than the fences of 230 because the max is less than your fence. Now, still looking at this can actually help me with some data here. It says one of the manufacturers advertises a cordless phone at only $31.95. Well, the problem with this is if I actually look at my box plot up here, 31 would fall above your first quartile. I could actually do the calculations on this if I'd like to figure out if it was normally a normal curve where it would be, but I could simply say that $31.95 lies within the second quartile. I could say at least 25% of the data or of the prices is less than the $31.95. So I would say no, that should not be a very low price. To me, something would be a very low price if either it was one of your minimums, or if, in this case we don't have any, if it was an outlier, would be something that I would explain to be a minimum. I'm sorry, for a low price. Draw and label a normal model. You want to put your normal curve, hopefully a little bit better than mine. You put your mean in the middle. 1, 2, 3. 1, 2, 3 for your standard deviations is 90. So 890, 980, 1070, backing up the other way, 710, 620, 530. And you must put your percentages on. 68%, 95%, 99.7%. And you must label your graph. So this would be clients who use the gym at a particular gym and we are talking about weekly. To calculate where the first quartile of the clients would be, that's the probability to find the value that's going to give you 0.25. So whenever you're given a probability, you're going to go to your inverse normal. Remember, you see how I clear out my screen here? Because if you have something accidentally in the line before your calculation, it will totally mess you up. So I'm going to say the inverse normal, 0.25, where the mean is 800. Oops, I hit the 8 in there. The standard deviation is 90. And so the first quartile would represent about 739, and if we wanted to put a decimal, fine, but don't go crazy because there's still people. The first quartile of the weekly number of clients is 739.3 clients. The inner quartile range, but we've already found the first quartile, so we would need to find the third quartile. So I'm going to do that again, but this time I'm going to change it to 0.75 as my lower number, and so that gives me 860.7. Inner quartile range represents the difference, so 860.7 minus 739.3, and so I get roughly 121.4 clients. Okay, moving along. We want to draw box plots for the competition times for students and for faculty. So that means I have to go from the smallest number being 3.75 to my biggest number being 25. I'm going to go 0 to 25. I'm going to count by 5. 10, 15, 20, 25. Okay, they give me my quartiles, which is lovely. They give me my median, which is wonderful. And we can calculate our inner quartile ranges as well. But let's start with the students. For my students, my median is 9.25. My lower quartile is 6.75. My upper quartile is 13.75. So if I take 13.75 minus 6.75, you get your inner quartile range, which is 7. So if I take my lower quartile, and I can already tell 6.75 minus 1.5 times 7 is going to go all the way below 0 to a negative, so I'm not going to have any lower outliers. So I'm going to just put my minimum up here because I don't have to worry about it. And for my upper quartile, if I take 13.75 plus 7 times 1.5 to find what my upper fence is going to give me, I get 24.25, which is well beyond my maximum, so I don't need to worry about plotting that. And I need to label this as students. I'm going to do the same thing for my faculty. Faculty have a median at 11. They have a lower quartile at 8.75. They have an upper quartile at 15.75. I want to find my inner quartile range, 15.75 minus 8.75, and it's actually sometimes quicker to just do the math in your head and get an inner quartile range again of 7. And again, I'm not going to go outside of my fence for my minimum. I can just tell by basic understanding. So if I go down to 4.5, that's where my first fence stops. And if I take 15.75, I believe again I'm not going to have any outliers, but it's good to do the math just to make sure here. 1.5 times 7. Sure enough, I get 26.25, which is outside of my data range. And so there's my faculty. Okay. And we're looking for completion times. So I need to put my label up here. This is completion times in minutes for an obstacle course. It says write a few sentences describing the variability. I am not going to fully write them out, but I'm going to bullet point for you some of your key points. For the key points, I would take a look at the faculty has greater variability. I'll write it out. Because if you look at it, the inner quartile range for the faculty and for the students was the same. But the overall range was significantly different. You can see that by the spread of data here. The range for the faculty from the maximum to the minimum was 20.5. The faculty, which was greater than the range for the students, max minus min, which was 12.75 for the students. Now that's describing variability. That wasn't describing anything further. I would say further that the faculty had a higher average and actually it had a higher both mean and median, so I'm just going to say average period than the students, and you would actually list out what your means are, what your medians are. I would also say that the faculty, because it's more variable, are less predictable. And I would say pretty much that the students kick the faculty's butt. Because if you should know anything about competing in a race, a lower time is better. Faculty was kind of a little bit on the slow side, but the students did significantly better. Hopefully this, in combination with your textbook problems, and please note the answers to the textbook problems are in the back of the book, should help you be on a good, solid foundation for your test.